The lesson today, we're going to talk about how to use chords. So as a review, when you've got a circle, a chord is a line segment that has endpoints on the circle. So this is one example. And there's a very special chord called the diameter, and it also is a line segment with its endpoints on the circle, but it has the additional restraint of going through the center of the circle. Okay, starting off the beginning of our lesson, we have got 3 proofs. The congruent corresponding chords theorem, perpendicular chord bisect theorem, and perpendicular chord bisect converse, which I'm not seeing that bottom one on our theorem sheet. So let me open up the theorem sheet and we'll get those written down with the example. So the 2 that I have that we're covering today, again, is the congruent corresponding chords theorem. So this one right here, you should already have this one filled out from yesterday. So it says chords either in the same circle. So in order for them to be congruent corresponding chords, they have to be in the same circle or on congruent circles. That's a must. It has to have that. So if that's the case, then the 2 minor arcs are congruent if and only if their corresponding chords are congruent. I hope you have more room than I do for this picture. So let's talk about this. I'm going to draw this one where they are, oh, Sam. I'm going to draw they're going to be in the same circle. So here's a circle, and I've got 2 minor arcs. So in order to create minor arcs, I'm going to have a chord here and a chord here. Let's call that B. Again, I hope you have more room than I do. C, A, and D. So let's go back and read this again. So I'm on the same circle. So these 2 minor arcs, this arc CD is going to be congruent to this minor arc BA if and only if the corresponding chords are congruent. So chord CD is congruent to AB. So these are connected together. You're going to look at pictures and it's either going to have this showing that those chords are congruent, and then we can conclude that the arcs are congruent, or it's going to start with the arcs are congruent and we will conclude that the chords are congruent. Okay, let me make sure I'm doing the right ones. Congruent corresponding chords theorem and perpendicular chord bisect theorem. Yes, I'm on the right thing. So again, if we need to pause and take the time to write that in there, let's go ahead and do it. Okay, perpendicular chord bisect theorem. It starts out by saying if a diameter of a circle is perpendicular to a chord, and notice it doesn't say if the diameter. There's more than one possible diameter. So any of them, if a diameter of a circle, and I decided I'm using that shortcut to the word perpendicular. I don't know if I put it on this page. Nope, it got erased. This is perpendicular. And it means 90 degrees. I've also been using this shortcut. This means congruent, which is the same measure in a different location. Okay, coming back. If the diameter of a circle is perpendicular to a chord, then the diameter bisects the chord bisects the chord and its arc. So take time, if you have to push pause, take time to write that down. And then again, I hope you have more room than I do. Here is my diameter though. I'm going to start, remember it's a special chord that goes through the center. Looks like a Pokeball. And then my second part is that I've got a chord that is going through it. So the diameter of a circle is perpendicular to a chord. So if that's happening, then the diameter, which is this one again, bisects. That means it's going to cut this chord into 2 equal pieces. And it also said it's going to bisect this arc, this minor arc. So I better give this some A, B, C, D. Oh. If CD is a diameter and EG, oh, I wrote that different on mine, and AB is perpendicular to CD, so that's this if. That's what's starting right here. If we've got a diameter and they're giving it a name and it's perpendicular to a chord, which we're giving it a name, AB, then, oh, I gotta name this too. A, B, C, D, let's see, E. Then AE is congruent to segment EB, and arc AD is congruent to arc DB. All right, I hope you, again, have a smaller handwriting, so push pause until you've written all that down. Okay, so how are we going to use that? Here is one way. So we've got these circles. And remember, when you see this, you read it in the diagram, circle P, so it's talking about this one, we're named off of our center, is congruent to circle Q. I think I skipped something. Oh, it was probably yesterday. Yesterday we hopefully learned that all circles are congruent that have the same radius. So notice we've got these here are showing me that I've got the same radius. So these are the same size. Let's see what else it tells us. FG, can you find FG, is congruent to JK. And again, I see the markings. They gave me that marking, so I know exactly what they're talking about. These are congruent chords also. The measure of JK, this arc JK, is 80 degrees, and the measure of FG is what we're trying to find. Well, if these are the exact same circle, so we're going back to congruent corresponding chords theorem. These are not the same circle. So the example that we drew was the same circle, but these are congruent circles. So in congruent circles, ding, 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 2 minor arcs are congruent if and only if their corresponding chords are congruent. So here's the arcs, and here's the chords. So FG would be 80 degrees. Now, I have to point something out. When it says the measure of FG, that is not the length. If I took a measuring tape and a ruler and I measured from here to here, that's not what I'm talking about. I know it sounds like the measurement or something, but length is going to be part of the circumference, and we'll do this another day. This 80 degrees is going along with this arc here would be 80 degrees. And this, angle here would be 80 degrees. So when it just says the measure, that's what it's talking about, is that central angle. Okay, let's look at this one. This theorem has that perpendicular, so I'm looking back to my theorems paper. Perpendicular chord bisector. My hint is that I've got a chord. It's intersecting a diameter at a 90-degree angle. That was kind of that if-then part of it. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and it bisects the angle. So if those are congruent, I can set up an equation here. So go ahead and solve that. But it says to find HK. I wish they were a little more fussy. HK is this chord. And I'm noticing as I look up here that I've got a 7 right there. I didn't notice that at first. So HK will be 14. And the measure of arc HK, well, it just says 11x. But I found x is 7. So it's going to be 77 degrees. Now remember, measure is not length. Measure is like a central angle. So if I were to come down here, I've kind of made a mess of this picture, but if I came down here at these two endpoints and I created an angle with the center, that's going to be 77 degrees. All right, so push pause, read this, see if you can figure this one out. 3 bushes are arranged in a garden as shown. So for those of you in the back, hopefully you can see these. That's not any better. 1 bush, 2 bushes, 3 bushes. Where should you place the sprinklers with the same distance from each bush? Good question. Okay, so does somebody want to come up and drag the circle on? So if the sub is going to do this on her own, you can have the students come up and drag this circle on. Okay, so we need to find the center of our circle. And if we want it to be able to hit all of them, right, it's got to be radius, radius, radius. So the center of the circle would be the best place that it would be able to be the same distance because all of the radii are congruent. Okay, we're going to do a few more practice ones to get you ready for your big ideas. All right, so again, we're going back to see how we can use these two theorems, congruent corresponding chords theorem, which for some reason looks like Hello Kitty on my picture, and then the perpendicular chord bisector theorem. Okay, so if the measure of AB is 110, and the measure of AC, I don't know how to do this, is going to be, I think I just skipped to another problem. Okay, find the measure of BC. Well, these don't look like anything perpendicular, so I don't think it's the perpendicular chord bisector theorem. This does look like I've got chords and arcs. So it's not exactly like my picture because ours were parallel, but it's the same idea. So in the same circle, check. 2 minor arcs are congruent if and only if their corresponding chords are congruent. Now remember, if and only if can go backwards. So these chords are congruent, so the arcs will be congruent. If AB is 110, BC will be 110. Okay, pause this and see if you can find that next bit on your own. Okay, hopefully you had time to find that one on your own. So this one's telling me the measure of AC is 150 degrees, and it wants me to find AB. Now, this is funny, I'm making these videos out of order because I wanted to be able to send it to the sub, so I'm hoping there's some things we learned yesterday. Since the chords are congruent, we know that the arcs are congruent, so I'm going to call this X and this X. So X plus 150. If you got stuck, see if you can figure out what the whole circle will equal. Maybe push pause again and finish it on your own. Okay, if you've unpaused, it's 360, so I can combine my like terms. I can subtract that 150 from both sides. Divide by 2. So on this second problem, and I know it's not matching this top thing up here, but they're two different problems. They're just giving us that generic diagram. X is 105, and that's what I named these arcs. So arc AB is 105 degrees. Okay, this is practicing our next theorem, this perpendicular chord bisector. I can tell because I've got a diameter, check. I've got a chord, check. They meet at a 90-degree angle, double check. Find the indicators. There's a lot of information over here. I know that these are going to be equal, so this will be 5. I know that these two arcs are equal because it's that theorem. So I can do 9x equals 80 minus x. And I just kind of started going over here. I didn't even see what they asked for. So maybe I'll come back and see. The first thing they want is CE. CE is this whole chord. If both of those pieces are 5, this one's 10. And the measure of arc CE, okay, I'm not quite there yet. I can keep finishing this. So I found x, but I'm not able to answer the question. What is the measure of arc CE? Any thoughts? Well, I need to add these arcs together. But everywhere I had an x, I'll put 8. X, 8. Go ahead and finish that. Don't forget to put degrees if it's asking for the measure of an arc. Otherwise, I might think it's the length. And a length would be a part of the circumference, whereas this 144, let's draw it over here. If I were to take these endpoints of the chord and make a central angle, that central angle is 144 degrees. Oh, we do have another theorem. I didn't even finish this one. Equidistant chord theorem. So on your paper, you need to write, and this is that box down below, in the same circle or incongruent circle. So this starts out the exact same as congruent corresponding chords theorem. So our picture is of the same circle, but they could be different circles. So two chords are congruent if and only if they are equidistant from the center. Only if they are equidistant from the center. So this and this would have to be the same as well. And remember, if and only if I could go the other way around. So I could start with if EF is equal to EG, so these distances, if they are equal, then AB, the whole chord, is congruent to CD. And congruent means they're the same measure in a different location. So push pause while everybody writes that. All right, let's do a practice with this. In the diagram, QR equals ST. So we've got two equal chords, and then it says that it equals 16 units. So I'm not really sure where to write that. Maybe just right here. Okay, we got more information. CU is 2x. Oh, that's already written in there. And CV, where's my V? Oh, it's also camouflage. CV is 5x. Holy cow. Oh, 5x minus 9. Oh, they also wrote that in already. Find the radius of circle C. So from what I can see, this is going to be a couple different problems. This is that theorem that we just went over, the equidistant chord theorem. So if you've got, let's go review it again. If two chords are congruent, which they showed us that, they are congruent, they told us the measure, 16 and 16, and then they are equidistant from the center. So these must be equidistant from the center. So I can set 2 x equal to 5x minus 9. So go ahead and solve that if you have not already. At any time, you just push pause if I'm going too fast. Okay, that's not quite helpful. If x is 3, and I know that from here to the center is going to be 6. Now, how do I find the rest of the radius? I want the radius. Well, I feel like this is a bit of a stretch, but if I take this end here and I connect it with the center, and I know that half of this guy, because of this perpendicular here, half of this is 8. So this triangle, I've got an 8, I've got a 6, and then this is my radius. I just swung one around. So this is how I think I would find it using the Pythagorean theorem. 6 squared plus 8 squared equals the radius squared. So again, push pause, finish this one. So this is a Pythagorean triple. And we've got that r equals 10. We've got lots of practice to get us ready for our big ideas. So in the diagram, JK is equal to LM. So again, looking back at those theorems that we just read about, if you've got two congruent chords, then the distance of those chords straight to the radius, so this one here and this one here are congruent. So I haven't even read forward to see what exactly they want me to find, but I know those are going to be congruent because of that theorem. Let me read it again. The equidistant chords theorem. It's if and only if. And so we're going to use this minus your 7x. So again, I don't even know what they're wanting me to find yet, but I'm pretty sure I'm going to need this x. So go ahead and finish this. All right, now I'm going to go look what they wanted me to find. So this distance here is 9. Find the radius of circle N. Okay, this is like the one just before it. Oh, except I didn't read that very carefully. JK equals LM equals 24. So if this whole entire thing is 24, when I go to create this right triangle that has a radius here, I'm going to use 12 and 9. So I might come and draw that. This is my radius. This is 12. This is 9. So use the Pythagorean theorem to find that radius. I hope all these different things are coming together. Okay, finish that on your own. Share your answer with your neighbor. All right, I got that the radius was 15 units long when I squared the legs and then square rooted everything. Okay, hopefully you're ready for those big ideas. I'm just going to leave this up on the board because if you get stuck, it's going to be on these radius ones where you have to kind of draw it yourself and create a right triangle. So if you're wondering, why are they giving me the measure of the chord? What does that have to do with the radius? It's going to be part of your right triangle.